In the endless expanse of the cosmos, stars stand as the brilliant beacons of our universe, captivating mankind's imagination for millennia. Hey guys, it's your friend Siddhant, and today I'm taking you on a journey through the cosmos as we unravel the mysteries of these celestial giants. For centuries, astronomers have studied the stars, unlocking their secrets and expanding our understanding of the universe. Yet, even today, the study of stars continues to push the boundaries of human knowledge. Stars are born from vast clouds of gas and dust, where gravitational forces compress matter, igniting nuclear fusion in their cores. This fusion process releases immense energy, which radiates outward, giving birth to the star's luminous existence.
The problem with going to the stars is only the first few hundred miles. If you can negotiate the first few hundred miles and get off the gravitational well of the planet Earth, you're well on your way to going to the stars themselves.
Stars can be classified into different types based on various criteria, such as their size, temperature, color, and stage of life. According to the spectral characteristics, stars are classified into 7 main types: O, B, A, F, G, K, and M. Now, one of the most fundamental ways we classify stars is through the Hertzsprung-Russell diagram, which plots a star's luminosity against its surface temperature. Main sequence stars. Main sequence stars are the workhorses of the universe, fusing hydrogen into helium in their cores to produce energy. This fusion process creates a balance between the inward pull of gravity and the outward pressure of radiation, keeping the star stable. The Sun, for instance, is a main sequence star, and it's about halfway through its roughly 10 billion-year lifespan. Main sequence stars make up around 90% of the universe's stellar population. They range in luminosity, color, and size from 1/10 to 200 times the Sun's mass, and live for millions to billions of years. Many main sequence stars can be seen with the unaided eye, such as Sirius, the brightest star in the night sky, in the northern constellation Canis Major. Red giants. Red giants are large, evolved stars in the later stages of their life cycle. Red giants form from stars like our Sun when they have exhausted their core hydrogen fuel. As the core contracts and heats up, the outer layers of the star expand and cool, causing the star to swell in size and become a red giant. While a star like our Sun has a radius of about 1 million kilometers, a red giant can have a radius tens to hundreds of times larger. Despite their expanded size, their mass remains relatively similar to their main sequence phase. This phase can last a few million to a few billion years, depending on the initial mass of the star. The Sun will become a red giant in about 5 billion years, shedding its outer layers, forming a planetary nebula, and leave behind a dense core called a white dwarf. White dwarfs. After a red giant has shed all its atmosphere, only the core remains. Scientists call this kind of stellar remnant a white dwarf. A white dwarf is usually Earth-size but hundreds of thousands of times more massive. A teaspoon of its material would weigh more than a pickup truck. A white dwarf produces no new heat of its own, so it gradually cools over billions of years. Despite the name, white dwarfs can emit visible light that ranges from blue-white to red. Scientists sometimes find that white dwarfs are surrounded by dusty disks of material, debris, and even planets, leftovers from the original star's red giant phase. In about 10 billion years, after its time as a red giant, the Sun will become a white dwarf. Neutron stars. Neutron stars are one of the most fascinating and extreme objects in the universe. They are stellar remnants that pack more mass than the Sun into a sphere about as wide as Indian capital of New Delhi. Neutron stars are formed from the remnants of massive stars after they undergo a supernova explosion. When a massive star runs out of nuclear fuel in its core, it collapses under its own gravity. The outer layers are expelled into space, while the core collapses into a dense, compact object. They are incredibly dense and have extremely strong magnetic fields, much stronger than those of ordinary stars. These magnetic fields can be billions of times stronger than Earth's magnetic field, and can have a significant influence on the behavior of the star. Neutron stars can be broadly classified into several types based on their properties and characteristics, including magnetars and pulsars. Pulsars. Pulsars have strong magnetic fields that funnel particles along their magnetic poles, accelerating them to relativistic speeds, which produces two powerful beams of light, one from each pole. Some pulsars spin faster than blender blades. The fastest known pulsar, PSR J1748-2446 AD, spins at an astonishing rate of 716 times per second. Magnetars. Magnetars are known for their extremely strong magnetic fields, typically ranging from 1,000 to 10,000 trillion Gauss. These are the strongest magnetic fields known in the universe. Magnetars rotate relatively slowly compared to pulsars, with periods typically ranging from a few seconds to several minutes. They are known for sporadic bursts of X-rays and gamma rays, often accompanied by seismic-like activity on their surfaces known as starquakes. These bursts can be incredibly energetic and are thought to be caused by the intense magnetic fields. Red dwarfs. Red dwarfs are the smallest main sequence stars. They're also the coolest, and appear more orange in color than red. When a red dwarf produces helium via fusion in its core, the released energy brings material to the star's surface, where it cools and sinks back down, taking along a fresh supply of hydrogen to the core. Scientists think some low-mass red dwarfs, those with just a third of the Sun's mass, have lifespans longer than the current age of the universe, up to about 14 trillion years. Brown dwarfs. Brown dwarfs aren't technically stars. They're more massive than planets, but not quite as massive as stars. Generally, they have between 13 and 80 times the mass of Jupiter. They emit almost no visible light, but scientists have seen a few in infrared light. Some brown dwarfs form the same way as main sequence stars, from gas and dust clumps in nebulae, but they never gain enough mass to do fusion on the scale of a main sequence star. Others may form like planets, from disks of gas and dust around stars. Brown dwarfs are more difficult to detect than stars because they are fainter and emit less light. They were only discovered relatively recently, and their study is still an active area of research. Quasi Star. Also known as a black hole, stars are theoretical objects proposed by astrophysicists to explain the potential formation of supermassive black holes in the early universe. These hypothetical entities are thought to have formed from massive primordial stars, which were much larger than stars we observe today. These stars would have been so massive that they could have potentially collapsed into black holes shortly after their formation. Quasi-stars are intriguing because they provide a possible explanation for the existence of supermassive black holes, which are found at the centers of most galaxies, including our own Milky Way. The exact formation mechanisms of supermassive black holes are still not fully understood, But quasi-stars represent one compelling hypothesis in this ongoing scientific investigation. From the fiery birth of new stars to the dark, silent graves of old ones, the universe is a stage upon which an endless drama unfolds. Each type of star tells its own story, shaping the cosmos in ways both beautiful and profound. Join me again next time as we continue to explore the wonders of the universe, where the mysteries of the cosmos await those who dare to seek them.